Okay, well, it's been a couple of weeks, so I should start by refreshing your memories on what we did last time. Now we're doing electrodynamics now instead of electrostatics, which we spent so much time on. And all that means, of course, is the electricity is moving now. And what physicists are discovering is that brand new effects that they didn't anticipate at all, they start seeing when they can set the electricity in motion. And what they're discovering is that there is an unanticipated connection between electricity and magnetism. That, remember before, at the stage, for instance, when Coulomb did his work, they were just studying static electricity and magnets, and they had this theory that in ordinary matter there is this electrical stuff, the electrical fluid, and there's a magnetic fluid, they supposed. Two different, completely different things. And so they, if you take that point of view, that leads you immediately to think that electricity and magnetism are unconnected. But now, starting with Ørsted, who discovered that when you have an electric current, it deflects a magnetic compass needle, they start discovering that there's this close connection between electricity and magnetism. I mean, the first major discovery was that an electric current exerts a force on a magnet, right? That's what's moving the magnetic compass needle. Then they found out that a magnet also exerts a force back on an electric current. Okay, and we talked about the direction of those forces. And Ampere was the one that came up with those two right-hand rules that allow you to always figure out what the direction of the magnetic force produced by the electric current is. Remember, that rule is just stick your thumb in the direction of the current, and the magnetic force is in the direction that your fingers curl. It goes around the current. And then we had a more complicated second rule that allows you to figure out how a magnetic force on an electric current will actually act to move the current. There you curl your fingers from the direction of the current. You point your fingers in the direction of the current. You curl them in the direction of the magnetic force, and that will be the force on the wire. Okay, so now using that rule, or actually using the first rule, where we have a current-carrying wire, say. Now, we started out with straight wires. Well, if you put your thumb in the direction of that current, the magnetic forces will go around it, right? In this case, in that direction. Okay, that's the direction that it will deflect a magnetic compass needle. Now, Ampere figured out that just using that simple rule, he thought, well, what if the wire isn't straight? What if we put it in a coil? We wrap it around a glass tube or something, make a coil of wire. Well, he figured out that the magnetic forces from that coil of wire with a current through it would act just like a magnet. So, what that means is that if you have a coil like this, and let's say the current is going counterclockwise through the coil as I've drawn it here. Then the lines of magnetic force, in other words, the force, the direction that it would push a north pole on a magnet, will come out of the top here. The magnetic force lines. And in through the bottom. And so that's exactly like what we would get if we just had a bar magnet with a north pole up here and a south pole down at the bottom. So a coil with a current through it acts just like a magnet. Now, this actually gave Ampere a revolutionary idea, because just prior to, I mean, the years prior to when Ampere's doing this work, which is, remember what these years are? Anybody? Yeah, Daniel.
1830s?
20s, actually. Yeah, early 20s, because remember, Oersted made his initial discovery in 1819. And it was shortly after that, by 1820, that Oersted's results had been published and presented to the scientists in France, and so a number of physicists in France went and started investigating this phenomenon, and Ampere was the most successful of those physicists in actually figuring out the laws and making discoveries. Now, so he's doing this. He starts in 1820, and in the next few years, he makes all of his basic discoveries. Now, in the decades just prior to this, there had been a lot of progress in geology, in figuring out, making major discoveries about the Earth and the way that land masses evolved. And one of the things that had been discovered, which people had suspected for a long time, was that the interior of the Earth is very hot. I mean, the most obvious evidence we have for this is volcanoes, right? I mean, volcano erupts, you get this molten lava that is thousands of degrees spewing out from the interior of the Earth. So, I mean, that gives you a pretty obvious evidence that the interior of the Earth is very hot. Now, we know the Earth is a magnet, and we also know that if you take a magnet and you heat it up to something over 1,000 degrees, it loses its magnetism. So the Earth can't just be like a normal bar magnet made out of iron. Yeah. Yeah. Oh, little magnets? Well, but even they, I mean, if you heated them up enough, they would lose their magnetism, right? So, but this discovery of Ampere, that you can basically make a magnet just with an electric current going around in circles, gives him an idea. And how is he going to explain the Earth's magnetism now?
He's going to use it as like he's going to use it as what? He's going to use electricity to explain it.
Yeah, I mean he's going to keep the idea that the Earth's core is made up mainly of iron, but instead of trying to say that the Earth's core is some iron bar magnet, basically, he's just going to say no, it's molten iron. I mean, it's liquid iron. The Earth is rotating. This causes that molten iron to sort of spin around in there and somehow sets up electric currents that go around like they do in a coil. Now, Ampere didn't have a complete theory of exactly how that worked, and we don't actually to this day have a good theory of how that works. But we know that somehow it does work like that, because that's the only way that the Earth can be a magnet, is by means of these electric currents, not by having a permanent bar magnet inside the Earth. So this is a whole new way of generating a magnet rather than just having a piece of magnetized iron. And it gave scientists a way of understanding how the Earth could be a magnet even though the Earth's core is several thousand degrees. Okay. Now, there was another implication of these discoveries that I've already told you about that Ampere saw. And see if you can guess what it is. I have to get rid of this. Oh. How come this isn't working? Okay. We have an eraser problem today. Okay. Let's think about what you already know and see if you can figure out the next major discovery here. Now, if a magnet exerts a force on an electric current, we know it does, and we know an electric current can act like a magnet. So magnets exert forces on electric currents. Electric currents can mimic magnets. So, Nick?
Can you make a magnet out of by putting it?
You can, yes, you can make a magnet with an electric current. I mean, that's one of the things that Ampere did, was he took an unmagnetized bar of iron, wrapped a coil around it, and sent a current through it. And that magnetized the bar of iron, turned it into a magnet. Okay, now, that's one thing, but that wasn't actually what I was looking for. Ben?
By magnetizing the bar, would it be like really powerful? Would the bar be a really powerful magnet?
Yeah, I mean, you could make a very, that's something else scientists would eventually do in the next 10 years or so, make extremely powerful magnets using electric currents. But I'm looking for a different force relationship than we've seen before. We've seen forces between currents and magnets, between magnets and currents. We've seen how a current can mimic the behavior of a magnet. Yes,
Maybe
try.
how we can make electricity from a magnet, or have it, like have a magnet have get an electric current?
Oh, an electric current through a magnet?
Yeah.
Well, I mean, you could do that. I mean, obviously, you can have a magnet that's made out of iron that does conduct electricity. But again, I'm looking for something else now, a different force relationship. Do you see?
Can the force of a magnet mimic the force of electricity?
Oh, okay. Well, let me put it this way. That's not quite what I was looking for either. Let's say we know that and one of the examples I gave you is if you have a wire, let's say you have a rectangular wire that you're putting a current through, okay? And the case that we talked about, let's say it's hanging on pivots up here. So it's hanging vertically. Okay, so it's free to move, free to swing. Well, you know that, I mean, we considered this case before. If we bring a bar magnet up to it, let's say we bring, let's see. Let's put a bar magnet right down here at the bottom with the North Pole near the the bottom of this rectangular current wire that's free to move. Now, what's going to happen with that wire? Let's, can you, yeah, Daniel. Okay, so we've got a current in this direction, so you put your fingers in the direction of the current. Where's the magnetic force? Line is in that direction, right? So Daniel's exactly right. Okay, the wire is going to push out of the board. Now, what will happen if we get rid of the bar magnet? And instead, put our coil here. Send a current through that in the counterclockwise direction that, like I drew on the board before. Well, we know that acts just like a bar magnet with a North Pole up here at the top, right? So what's going to happen? Same thing. It's going to push the this wire out from the board, right? But now what have we shown? I mean, this is a different kind of relationship here. Ben.
We've shown that electrical current and magnets can act the same, like they're
Yeah, we're showing that, but we've got a force between what and what?
Electricity and electricity.
Yeah,
Electricity.
right, exactly. We've got a force. I mean, we've gotten rid of the magnet altogether. And we've discovered that electric currents exert forces on other electric currents. You don't need a magnet at all. Okay, so Ampere decides to investigate this. you can see how, I mean, this is a perfectly logical conclusion that has to follow from the discoveries that he's already made, right? I mean, given the fact that currents and magnets exert forces on each other, and the fact that an electric current can act like a magnet, produce its own magnetic forces, then currents have to exert forces on other currents. Okay, so Ampere starts to look at this, and he uses this setup that I've drawn here, where he's suspended this rectangular, so he's got a battery up here, and he's got a rectangular piece of wire that he has just hanging down, and so it's free to move. It can swing back and forth. Now he now tries, he says, well, forget the coil for a minute. Let's examine an even simpler case. What about two straight wires parallel to each other, both with electric currents in them? How will they act on each other? I mean, that's the simplest possible case, right? Just take two straight wires, put current through them, put them close to each other, and see the forces that they exert. Now, let's say, so what he does, he's got this rectangular loop of wire hanging down and free to move, and then, say, behind it, he's got some long immobile wire, okay? And it's not clear from the way I've drawn it on the board, but he puts these at the same level, okay, the same horizontal level. Now,
Which
right.
direction is the current going now?
I was just going to say, let's start them out with current in the same direction in both wires. Okay, because my drawing is so bad, make a note to yourself that these are supposed to be at the same level, that it looks like this wire is just above the other one, but I actually want it to be, say, in back of the other one on the same horizontal level. Okay. Now, what's going to happen? Well, you've actually got all the information you need to figure out what's going to happen. First, you figure, okay, this current here in the wire that can move, okay, it's going to respond to the magnetic forces produced by the other immobile wire, right? So the first thing to do is figure out what's the direction of the magnetic force from the immobile wire at the location of the mobile wire. Okay, so Troy, you got it?
That way, kind of going into the board.
Okay, let's think about it. We got, oh, you're still thinking of this wire above this one. Okay, remember, I've got it behind this one, right?
Oh, no, then it's going up.
So, okay, put your thumb in the direction of the current, curl your fingers, and that tells you the direction of the magnetic force from that immobile wire. Okay, it's going to be down, right? Fingers point. I wish, okay, I should, here, let me do a side drawing then. If I just look at, if I turn this whole thing, if I rotate it this way, I've got two wires with currents both into the board. Okay.
Okay.
Now, this one, say, is mobile. This one is fixed. This is supposed to be behind. So I've rotated it this way. Okay, everybody see? I'm sorry, I'm not a better artist. But so, I mean, this is the rectangle one that's free to swing back and forth. Okay, now, so point your thumb into the board. Where do your fingers go?
Down.
At the location of the mobile. Okay, so there's the magnetic force, the direction of the magnetic force. So now how do we figure out which way this wire is going to move? Ben?
We point our fingers down.
Point the fingers in the direction of what?
The current.
Fingers go in the direction of the current. So they have to go into the board and then curl them in the direction of the magnetic force. Right. It's going to go to the left toward me. So that's the direction of the motion. It's, in other words, if the currents between two parallel wires, if the currents are in the same direction, it's an attractive force between the wires. The wires will move together.
But why would it be going down? Because if the current's this way, wouldn't it be wrapping around it?
Yeah, the magnetic force, say due to the current through this fixed wire, is going around in a circle around that wire, right? But at this location, it will be pointing down because it will be going in a clockwise circle, right? The thumb, if the thumb goes into the board, then your fingers wrap this way. So that tells you that the circle is clockwise, and since the mobile wire is in the 3 o'clock position, it'll be going down in that position. I mean, if the mobile wire, if I'd put it over here, it would be going up, right?
So a compass needle would point down if you put it in that.
Yeah, exactly. That's what I mean whenever I say, you know, the magnetic force is in a certain direction. Remember that what I mean by that is that's the way it'll push a north pole. Okay. Well, so let's actually write down that result. So let me see. Write in your notes for well, you can call this this whole experiment. Let me see. Study of forces between currents. And the first conclusion we reach from this is that two parallel currents attract each other. Now, if this fixed wire, I mean, if that were mobile too, I mean, if we had two hanging rectangles here instead of, I mean, Ampere actually used one fixed wire and one that could move. But, I mean, he could have used two that were both mobile, right? And he would have seen them both come together. So the force that one exerts on the other is equal and opposite to the force that the second one exerts on the first. So there's an attractive force between these two parallel currents.
If the force was powerful enough and they touched, would anything happen, or would it just stay continually going?
No, if it were strong enough to bring them together, they would just stay together. It wouldn't be like the electrostatic case where, you know, when they touch, there's a transfer of electricity and then they repel. Because notice in this case, both of these objects, neither one of them has like an excess or deficiency of electric fluid, right? They're both neutral objects. All we've done is we've used a battery to set the electricity in motion. And just due to the fact that the electricity is in motion, we find that there are these new forces. The electricity in motion causes and exerts force on other electricity in motion, even if both objects are electrically neutral. Okay, now, what's going to happen if I say switch the battery here? In other words, now I turn the battery around so the current goes in the other direction. So now I'm going to diagram that by a little dot in the center of my circle, which means that the current is now coming out of the board. Actually, let's make that a general rule for my diagrams, which is that this means into the board and this means out of board. Okay, now what's going to happen? Sayla, do you have an idea? On what, if we just reverse the current on one of the wires now. Okay, now we're going to go through the exact same procedure again. Okay, so we do it the same way we did it before to figure out, now we haven't changed the current in the fixed wire at all. So we're still going to put our thumb into the board, right? Curl the fingers down, so the magnetic force is still going to go down. But which way is the wire going to move now? Hmm? Yeah, you just have to, yeah, you pointed the right way. But you just have to do the rule, right? Point your fingers in the direction of the current. Okay, this means, this dot in the center here means the current's coming out of the board now. Curl your fingers in the direction of the magnetic force, which is still down. And it pushes the wire out to the right now, away from the other wire. So what's the second conclusion? Troy.
Two currents going in opposite directions repel.
Yeah, exactly. So two, let's just say, anti-parallel currents, which just means exactly what Troy just said, which is currents going in the opposite direction, repel each other. Amazing, huh? Okay. Now everybody gets that. JJ, you know how these right-hand rules work, so you can figure that out. Okay. Now, like I say, this is there's no. I mean, if we think in terms of Franklin's old theory, I mean, all these results would have surprised Ben Franklin. I mean, he thought of electricity as just electrical forces arise when there's an excess or deficiency of the electrical fluid in a body, above or below the normal amount of fluid. Well, here we've got two electrically neutral objects. All we have to do is set the electricity in motion, and we get these forces between electrically neutral wires. Which will turn out to be very, very useful. Okay. Now, what haven't we seen so far in electrodynamics that Coulomb accomplished for the field of electrostatics? I mean, remember, we learned a lot about electrostatics. I mean, there were two kinds of electricity and so on and so forth, before Coulomb came along. But what did Coulomb supply that his predecessors didn't know anything about?
The relationship with distance.
Yeah, exactly. What we don't have so far is any math, right? No mathematical laws, no investigation of how these forces depend on distance and how they depend on the magnitude of the current. So that was the next obvious thing for physicists to investigate was, well, can we come up with a law like Coulomb came up with for electrostatics? Okay, so how would we do that? Well, turns out you can actually take Coulomb as your guide here and do a similar type of experiment in this case. Let's go back. So let's call this, let me see, search for the mathematical law. Okay, now let's go back to the first simple experiment that anyone did. Go back to Oersted's original experiment, or Ampere's version of it, where you remember what, say you have a vertical wire with a current going up, and let me see, let's say you've made a little hole in your laboratory table here, and you've got your wire going through that hole. And then you put a little, let's say you put a little pivot here and put a compass needle that is oriented, say, into the board. On your table. Magnetic, or let's just say magnetized needle. Okay, now this is just the original experiment, right? Where you have it, if you have a magnetized needle on a pivot, so it's free to rotate in the presence of an electric current through a wire. And we know now that if we point the thumb in the direction of the current, wrap the fingers around, okay, so the magnetic force will be into the board, which means that the needle will be in the orientation that I've just drawn it. In other words, the north pole of the needle will line up into the board with its north pole into the board in this case. Okay? Now, how are we going to figure out how what we would like to know is how the strength of this magnetic force varies with distance from the wire, right? And with the magnitude of the current. Okay, but let's start out talking about distance. How does it vary with the distance? Now, Coulomb did an experiment something like this, if you recall. He didn't, and there were no batteries at the time, and there was no electric current, but he tried to figure out the strength of the magnetic force. How? Does anybody remember? Evan? Well, with the he used his torsion balance for the electrical repulsive force. That was what he started out doing. But remember that what happened to him when he tried to investigate the attractive force was the little charged balls kept flying together. And so he made up a different way of doing that. Yeah, the pendulum. And so Coulomb, remember, showed that if I take this magnetized needle on a pivot and I displace it from the direction that it wants to be pointing in this, the magnetic force is forcing it to point into the board. Well, if I displace it from that, what will happen? It'll swing back and forth, right? Just like gravity makes this swing back and forth. And we know that the rate that it swings back and forth is determined by the strength of the force. Right? So it gives us a direct measure of the strength of this force by doing this. Well, actually, it wasn't Ampere that did this experiment. It was one of his colleagues.
Should we write his name?
Yeah, I can give you his name. I can't remember his first name, but this was Biot, I think is how you pronounce that.
Did he use Ampere's information to try this?
Well, he was familiar with Orsted's work, and he was familiar with Ampere's work. But he was working while Ampere was just was doing his investigations too. So it wasn't after Ampere's work; it was at the same time. Right.
When did you do this, or like? What
Oh,
years or something?
This actual experiment was in 1820, I believe. No later than 1821. Oh, we're done. So I will continue this in the afternoon.